Hello, my name is Matthew Vigil, and today I will be presenting on the development of electrochemical methods for in situ diagnostics of fluids, impedance spectroscopy, and cyclic voltammetry. I work in MPA 11. One application that we are currently developing these methods for is a water desalination process. Currently, as part of an LDRD project, we are working on a desalination process using supercritical water, a state notorious for being difficult to contain and make measurements in due to how corrosive water is. We need a robust method to measure properties of the water before, in situ, and post-process, to characterize the bulk water non-destructively while extracting valuable minerals. By measuring bulk solution properties such as conductivity and permittivity, we can know how pure the water is in terms of electrolytes as well as its density. This can easily be done with impedance spectroscopy. However, as a side goal, we have attempted to distinguish ions from one another using electrochemically measured interface phenomena, using both impedance spectroscopy and a new technique, cyclic voltammetry. In order to non-destructively measure solution properties, we have investigated impedance spectroscopy and cyclic voltammetry. Impedance spectroscopy utilizes a two-electrode configuration and can measure bulk conductivity and permittivity, interfacial phenomena such as the electrical double layer, corrosion of metals, and we use an equivalent circuit model to extract these. Whereas cyclic voltammetry utilizes a three-electrode configuration and can measure Faraday currents, oxidation and reduction potentials, adsorption, corrosion of metals, and its TAFL analysis is used to do this. So the go-to technology for composition measurements is inductively coupled plasma mass spectrometry, which is well established and accurate. However, it is expensive, it destroys the sample, and it cannot be done inside of a supercritical water reactor. Here we can see the electrochemical cell hooked up to a 1260 solartron frequency analyzer. The two electrodes are made up of either platinum, the workhorse of electrochemistry, and hastelloy C276, a robust nickel alloy, known to be non-corrosive. The solutions are prepared with either 18 megaohm or distilled water, and consist of single electrolytes, either common salts or rare earth elements. Impedance is measured as a complex number, which has real and imaginary components. The real components tell us about the solution's conductivity, as we can see here in this graph, whereas the imaginary component tells us about the dielectric constant of the water, as well as interfacial phenomena using these critical frequencies seen on the graph. I looked at how applying an electrical bias to the system affected the interfacial critical frequency in order to develop a method for distinguishing aqueous electrolytes. So, if we take a closer look at our impedance spectra, plot the real versus imaginary component, and what is known as a Boyd plot, we can begin to think of our system as an electrical circuit. When the line touches the x-axis, the response is purely real, and this tells us about the resistances in our system. When the function is at a local max, the system is at resonance and is used to calculate the capacitance of the system using a circuit element. Here we have an interfacial resistance in series with a parallel capacitor and resistor for the bulk solution, as well as a parallel constant phase element and a charge transfer or adsorption resistor. The constant phase element I have used is the Havelock-Negami impedance, which is known to accurately predict non-ideal capacitor-like features in a circuit using a symmetry parameter known as alpha and beta. These will be investigated for their ability to distinguish electrolytes when a bias is applied to the system. When our circuit model is fit to the impedance spectra, we can see that it accurately predicts solution properties using both hastelloy C276 electrodes and platinum electrodes, even though they have different interfacial resistances. This method can reliably be used to characterize the macroscopic properties of the solution and needs to be investigated in the supercritical phase of water. In order to distinguish aqueous electrolytes from one another, we look at the impedance spectra of our solutions containing each electrolyte in the same bulk conductivity, and made 5 measurements of each spectra, then used the average and standard deviation to see what kind of overlap we have. The greatest difference is seen in the low frequency region, known to be associated with adsorption and double layer capacitance. So we applied the bias steps shown earlier and focused on the imaginary component of the impedance to look for resonance shift into a higher frequency region, where the Havelock-Negami impedance parameters could accurately predict the spectra. The alpha and beta parameters seem to be ion specific, but these differences are very small, and we are working on advancing our electrodes to enhance our detection sensitivity. Here we can see a plot of the alpha and beta parameters for each of the electrolytes. Small differences can be seen, but more experiments need to be done. If we look at cyclic voltammetry, we can see that the cell is much different than impedance spectroscopy. It's a 3 electrode. So I specifically looked at copper 2 sulfate and how it is affected with increasing concentrations of various supporting electrolytes. Here one can see the electrochemical cell, which uses a working electrode, which is glassy carbon in this experiment, a silver-silver chloride reference electrode, and a platinum counter electrode. The solutions are prepared with distilled water and 0.005 mole copper chloride. Various concentrations of supporting electrolyte are added and the voltage is swept from negative 1.2 to positive 1.2 in a clockwise fashion, which causes the copper to be absorbed and reduced and oxidized on the surface of the working electrode. If the supporting electrolytes affect the adsorption process in a way that is ion specific, we hope to absorb its behavior. From our experiment, we collect voltage current information, and we can see that first, the copper is adsorbed to the electrode and reduced before it is reduced further. Once all of the copper in the vicinity of the electrode is adsorbed and reduced, it is then oxidized and deadsorbed from the surface. If we add different supporting electrolytes and measure the response, we can see differences from electrolyte to electrolyte. One way to analyze the data is to do TAFL analysis in regions where it is applicable. We take the log of the current density and measure and fit the TAFL equation to the linear region here. We can then extract parameters such as the exchange current density, which describes how much current is passed for a single reaction, and the transfer coefficient, which describes how symmetric the activation barrier is for the reaction. If the supporting electrolytes have any effect on the copper reactions, it would involve these parameters. We look at various concentrations, and here is our results. The data is promising, however inconclusive, at this stage because I was not able to reproduce my experiments due to COVID-19. The method has been developed, and now experiments are needed to test its accuracy. In conclusion, the impedance spectroscopy is fully able to characterize the fluid based on bulk conductivity and permittivity using a circuit model. Interfacial phenomena used to distinguish ions needs more experiments to fully test its accuracy. Cyclic voltammetry is able to detect oxidation/reduction potentials, and TAFL analysis is a candidate for distinguishing ions. In the future, I would like to carefully reproduce more experiments for both impedance spectroscopy and cyclic voltammetry. We need to test its ability in the supercritical phase and detect rare earth elements, both of which require the development of electrodes that can withstand the harsh environments and reduce the potentials of rare earth elements into the window of potential with no electrolysis. This will enhance our detection abilities and allow us to optimize our desalination process. Thank you for your time today. Special thanks to the following: the DOE for funding the SULI program, the Student Programs Office for all of their help in allowing me to continue my research, my mentor Dr. Alp Findeglu for continued support, my colleague Dr. Tae-Jun Yoon for contributing Monte Carlo algorithms and his continued support throughout my internships. Thank you.